Okay, so this is just a little website which I found when I was thinking about something completely different. And you might like this, you might not like this, but to me, it really kind of gives you some good, kind of strong visualizations of what effect size is. Remember, effect size is different from significance. Significance is simply the likelihood that a particular effect is going to be due to chance. So the smaller that p-value, the less likely your result is to be different due to chance. But effect size gives you some indication of how strong that effect is, and it can be the case that you can get very weak effect sizes, which aren't particularly interesting, even when it's significant. Now, Cohen provides a handy little table in which he says something like, anything less than 2 is a weak effect, anything about 5 is moderate, and anything over 7 is strong. But still, it's kind of like a bit, it depends upon your particular purpose, it depends upon the research. Because clearly, if a drug it improves people's survival rates by 2%, then that might be significant. But if it improves their well-being by 2%, then that might not be so much of a problem. So it's trying to contextualize that. So this website, which I've got a link to on the in the topic 4 area of the Blackboard site, is actually something about, is a good way of visualizing this. So it's Cohen's D. Cohen's D, remember, D is basically stands for difference, and it's a difference between the two groups measured in units of standard deviation. So there's a little blurb here which is kind of nice, where it comes up with a problem of just coming up with strong, weak, medium in tables. And what we've got here is a nice little tool which shows two distributions here, and this kind of shows the overlap of the two distributions with a small effect size. So Cohen's D looks at 0.2. You can see that there's not much overlap for a weak effect. This light blue group here is doing better, presumably, on whatever it is, it's scoring higher than the dark blue group, but it's not a huge amount. There's a lot of overlap. There's a lot of situations where you can't tell the difference between the two groups. Only in this little pale blue here, this little strip down here, only there where the people in the light blue group are always outscoring people in the dark blue group. But what's nice about this is you can play around with it. So you can say, let's find a Cohen's D of 0.7. Now 0.7 is a big effect size. As Cohen would say, this is a strong effect size, and you can see that the distributions have got a bigger overlap here, but there's still a lot of smaller overlap, bigger difference. That means that the right hand group is bigger than the left hand group by 0.7 of a standard deviation. But down here are some other measurements which I've not talked about, and we don't care what these are, but there's a lovely thing I think really helpful called Cohen's U, U3 here. And what this does, it changes the text. So it says here, with a Cohen's D of 0.7, 76% of the treatment group will be above the mean of the control group. Okay, and then it goes on to describe these other things as well, which might be quite helpful. But to me, that gives a nice kind of summary of what these rather abstract numbers mean. So Cohen's U3 is quite a nice one there. So this text actually changes. 0.7 is among some of the biggest effect sizes in psychology, and one of the ones that I know about this because I've read quite a lot of research on this is that males are much more interested, according to evolutionary theory, in casual sex than females, and that difference is quite a big effect in psychology, a strong effect of 0.7 among some of the biggest effects in psychology. So what does that mean? Well, it means that 76% of men have got more of an interest in casual sex than the average woman. But then flip it over. That also means that 24% of women have got more interest in casual sex than the average man. So it kind of gives you, I think, a neat and helpful way of trying to summarize this thing. Another sex difference, I apologize for this just happens to be the kind of stuff that I'm compelled to write books about. The human difference in height is something like 1.4, which is a huge effect size. So the males are taller than females, but we can see there are some females that are taller than males. So what does this mean? Well, 1.4, 92% of men are taller than the average woman. But that also means that 8% of women are taller than the average man. So I think this tool can be useful. If you ever come up against effect sizes and start wondering, well, is this really big within the context of what I'm talking about? Or is this, even though Cohen says it's big, is it kind of small? Then have a look at this. There are other measures here. Probability of superiority. So it means that if you pick a person at random from the treatment group, it will have a higher score than from the control group. So what basically means, if you pick a person, you've got a bunch of 100 men and 100 women, if you pick a person from that group, then there's an 84% chance that that person will be a male who's taller than the women. So different ways. I just have a look at this and see if you find it useful, as I've done, for trying to interpret effect sizes.